Hello, this is my lab report for lab 1 regarding constant velocity. So the problem you're trying to solve is essentially comparing the movement of a real object in real time with a computer model coded in GlowScript. And the overarching fundamental principle is Newton's second law, which essentially states that if there's an acceleration, there must be a force, and the force depends on the mass times the acceleration. And if we derive that formula, we eventually reach this velocity update formula. We will code this velocity update formula and this position update formula into GlowScript in order to create the computer model that depicts the real object's movement over time. And essentially, this is a very interesting thing to do because, well, if we can code it into GlowScript, we can essentially use this model to model any object's movement over a certain period of time. So the organization of this lab report is essentially this. First, we'll watch a tracker video to understand what we were working with. And while doing that, we will address the total pushes and pulls experienced by the ball and also address if the axes were interchanged. Then we'll look at the GlowScript code and understand what it is doing. Then we'll compare the two using a spreadsheet. And then we'll also discuss the discrepancy between the model position and the experimental position. So first, let's look at the tracker video. So here we have a white ball moving at constant speed. We can see that the movement is relatively linear, and then we have data points regarding over time and the distance it traveled over those different periods of time. So for the short period of time, we could see that the movement could be viewed as constant because it seems that the white ball is moving at a relatively constant speed. This means that the net force on the object is 0, which would be prevalent for the model. But this doesn't mean that there are 0 forces. This just means that the net force is 0, which means that the forces could cancel out. So a question that can be asked is how many pushes and pulls are on the ball? And I believe there are 4, as shown here. The down force in the negative y direction would be gravity, and in the positive y direction would be the normal force, where essentially the ball can sit on the floor because when there's a force, there is an equal and opposite reaction. So that's why the ball can just sit on the floor normally. So now looking at the positive x and negative x direction, we can say that the force in the negative x direction right here would be the friction force, and the direction in the positive x direction would essentially be the ball pushing against the floor as it is rolling. And ultimately, the positive y and the negative y will cancel out, and the positive x and the negative x will cancel out, which will ultimately achieve a 0 net force. But we can also notice that the ball is not completely round, which will help us explain the discrepancies we'll see later in the video, in the lab report. So let's ask ourselves, what if the axes were interchanged? Essentially, let's say the positive x-axis was now the negative x-axis. Well, instead of a positive slope, we would have a negative slope. And we could see what it would probably look like here. As time goes over, the position goes from 0 to some negative x over time, and it stays relatively linear because, well, it would be a relatively constant motion. So the ball would instead be going into the negative x direction, but still be at its constant velocity. So now let's check out the GlowScript code. So here is the GlowScript code. We have a ball mass of a relatively 0.04 kilograms. Here we have our initial position vector, our initial velocity vector, and we chose a delta t of 0.01 seconds. Now back to the slide. We can see that Newton's second law of motion is applied, where we derive essentially F net is equal to dp over dt, and eventually we reach the velocity update formula shown here. And this code applies this exact formula and then the position update formula, as we showed previously, to model the ball's movement over time. And here is where we put in those two formulas and eventually reached our model. The ball's position is updated every 0.01 seconds until it reaches 0.604 seconds, as we saw before in the while loop. And since the F net equals 0, the ball's mass doesn't matter. And so essentially, this entire part essentially is equivalent to 0. So you saw I had an initial velocity of 0.73 in the x direction in the code. And how did I get it? I essentially used the position update formula stated previously right here. And since we're assuming constant velocity, I could take any 2 points from the tracker video and find the v average as shown in the formula right here. So I used the first 2 points that we saw in the tracker video, and then I eventually reached a 0.73 meters per second as my v average to get my initial velocity and put it into the code. So here's a spreadsheet where data was copied from both tracker and GlowScript to give us this line graph showing our experimental position versus our model position over time. And we can see that the dotted line is the experimental position and the straight line is the model position. And of course, we can see that, well, it seems to be pretty good, but up to 0.4 seconds and beyond, it starts to have some discrepancies. And essentially, this can be shown that that the explanation could be that the ball is not perfectly round, which leads to a not constant motion as it moves more bumpily, or the ball doesn't move perfectly straight and could have rolled slightly to the left or the right, or perhaps the camera was unable to pick up every minute change in its fixed captured frame rate. And in an ideal world, we would have a camera that caught infinite frames and observed every movement. Thank you.